46 years ago, Mount St. Helens killed 57 people in the worst volcanic disaster in American history. This week, the same mountain is shaking again. A cluster of small earthquakes has been registering deep beneath it, and government scientists who watch this volcano around the clock are choosing their words carefully. Not panicked, not dismissive, careful. That carefulness is the tell that something worth paying attention to is happening, even if it is not the thing you're picturing right now. In the next few minutes, you're going to learn exactly what this new activity is, and how scientists who study Mount St. Helens for a living tell the difference between routine background noise and the opening act of a real eruption. Those two things can look almost identical to an untrained eye and almost nothing alike to a trained one. Mount St. Helens sits about 96 miles south of Seattle, and it is, without argument, the most dangerous volcano in Washington state. Not the tallest, not the most photogenic, the most dangerous because of what it has. Already done once and what it is built to do again. Every few years, this mountain produces a burst of small earthquakes. And every few years, a wave of concern follows because the internet remembers 1980 even when it does not remember the geology behind it. This week's swarm is the latest version of that pattern, and it deserves a real answer, not a reflexive one. The first thing to understand is that Mount St. Helens is not a bucket of lava sitting under a lid, waiting for someone to take the lid off. It is the visible tip of a plumbing system reaching miles into the crust beneath it. Deep down, near the boundary where crust meets mantle, molten rock forms and begins a slow migration upward. Along the way, it collects in a storage zone a few miles beneath the surface, the mountain's engine room. Everything interesting at the surface, the earthquakes, the ground movement, the gas releases, traces back to that hidden chamber. When new molten material pushes into that reservoir from below, geologists call it recharge, the same way a battery recharges before it can be used again. Recharge pushes outward on the surrounding rock, and stressed rock does one very specific thing. It produces small earthquakes, clustered in time and space. Scientists call this pattern a recharge swarm. A recharge swarm is not the sound of magma breaking through toward daylight. It is the sound of a reservoir refilling several miles. Underground, gently pressuring the rock that contains it. The earthquakes are a symptom of the mountain feeding itself, not a symptom of the mountain about to erupt. That distinction matters more than almost anything else in this story, so hold on to it, because we are going to test it against the historical record in a minute. Before anyone lets their imagination run ahead of the facts, it helps to know exactly how small these earthquakes actually are. The magnitude scale is not a straight ruler where each number is a little bigger than the last. It behaves like a staircase, where every full step represents a massive jump in energy, released. An earthquake under magnitude 1 is not a gentler version of the kind you'd feel in your house. It is thousands of times weaker, existing almost entirely as a squiggle on a sensitive seismometer. A person standing directly above one, on the mountain itself, would never notice it. Not a shaking mountain, a whispering one. That is exactly why location matters more than raw numbers. 100 tiny whispers a couple of miles beneath the surface tells a completely different story than a handful of sharp, shallow cracks just a few hundred feet under the crater. One is a system slowly rebuilding itself far below. The other is something moving toward you. Depth and character, not head count, separate a routine week from the beginning of a real emergency. That brings us to the number that tends to spark the most suspicion whenever a swarm like this makes headlines. The gap between what the official catalog reports and what people staring at raw seismograph traces claim they can see. Here is how that gap usually plays out. Monitoring networks formally locate and publish a certain number of earthquakes, sometimes a small handful. But independent observers, people who pull up the unfiltered seismic traces and count every visible wiggle, often argue the true number is far higher. So which is correct? Both? And understanding why is the best way to protect yourself from the conspiracy version of this story, the one that inevitably starts circulating within hours of any volcanic swarm making the news. The claim goes something like this. Agencies are hiding earthquakes, and for every one they publish, dozens more are being buried to avoid causing panic. It's compelling because the raw traces genuinely do show more activity than the catalog lists, but that gap is not suppression, it's physics and arithmetic. For an earthquake to be formally located, the same signal has to be picked up cleanly at multiple stations and triangulated within a tight margin of error. A micro-earthquake, too faint to register at more than one station, simply cannot be located with confidence. And it's not just earthquakes competing for space on that instrument. Wind through trees, rivers rolling boulders, distant traffic, cracking ice, and the faint arrival of large earthquakes. From across the planet, all show up as noise on the same equipment. Force every wiggle into the catalog, and you wouldn't get a fuller picture. You'd get garbage that undermines the credibility of the real events. Here is the detail that quietly dismantles the cover-up narrative. During a nearly identical swarm in the past, the network monitoring this exact mountain stated plainly, unprompted, that many more small events were happening than could be formally located. The catalog was never presented as the complete truth, only as a conservative floor. The uncounted quakes were never a secret. That transparency is the best rebuttal there is. It helps to understand why a raw seismic trace looks so chaotic to someone who has never seen one before. A seismometer records every vibration that reaches it, not just earthquakes, wind-bending trees, a river tumbling stones, a distant truck cracking ice, even the faint ringing of large earthquakes from the other side of the planet. Buried inside that constant hum are the actual micro-earthquakes scientists care about, and the network's job is to pull that signal out with enough confidence to place a dot on a map. When an event is too faint to clear that bar, it does not vanish into a locked file. It simply stays below the threshold of certainty, visible as a wiggle, but not solid enough to call. The catalog is deliberately conservative. It would rather miss a genuine whisper than manufacture a false one. If this week's activity feels unprecedented, this exact mountain did almost exactly this 10 years ago, and nothing came of it. Starting in March of that year, Mount St. Helens produced a cluster of small earthquakes for roughly 2 months. The network formerly located well over 100 at depths of 1 to 4 miles. And again noted, many more were too small to pin down. Magnitudes were tiny throughout, mostly a half or less, with the largest only about magnitude 1.3. At its peak, the swarm produced close to 40 located quakes a week. That sounds alarming until you look at what accompanied it. Essentially nothing. No unusual gas, no ground swelling, no shallow earthquakes creeping toward the surface. The monitoring agency reviewed that episode afterward and stated flatly there were no signs of an imminent eruption. What they were seeing was recharge, the reservoir slowly refilling as it had many times before, a process that can continue for years, even decades, without ever producing an eruption. Recharge is not a promise of imminent activity. It's ordinary maintenance. It's worth being honest about what eventually happened at the end of the mountain's last long stretch of quiet recharge. When it erupted again, it was nothing like the catastrophic blast everyone associates with this mountain. It was a slow, grinding extrusion of thick, pasty rock piling into a growing dome over several years. Spine after solid spine, dangerous up close and monitored continuously, but nothing like the sideways explosion that made it famous. That's the actual range of outcomes recharge can build toward, and most of the time what comes out the other side looks more like a construction project than a detonation. We know this because the mountain recharged quietly for close to 2 decades before that eruption arrived. So when you hear this volcano is shaking again, the correct mental model is not a countdown clock. It's a mountain doing the same slow, patient underground work it has repeated for decades. But that still leaves the other half of this week's puzzle, the part nobody can look at without doing a double take. Because while these small earthquakes have been registering, the surface of the mountain has not been rising. It has been sinking. Here is the paradox as plainly as possible. The reservoir far beneath appears to be actively refilling, and yet the ground above it is measurably settling downward instead of swelling upward. A tank filling up should bulge outward. Instead, instruments on this mountain have recorded years of gradual subsidence. For a lot of people, this is exactly the detail that feels like proof of a cover-up because it seems to violate common sense. It doesn't, and the explanation is arguably the single most important idea in this entire story. The volcanic system beneath this mountain operates on 2 levels that are not rigidly locked together. Far below, the deep reservoir can genuinely be repressurizing, taking on fresh molten material like a battery charging. Scientists have directly documented this at this exact mountain in the years following its last eruption. The reservoir slowly reinflating even while the volcano sat completely silent at the surface. That's the charging half, happening deep and out of sight. Now the shallow half. The young volcanic rock this mountain built during its most recent eruption is doing exactly what freshly erupted rock does after it stops flowing, cooling, crystallizing, releasing trapped gas, and settling under its own weight, the way a loaf of bread deflates slightly as it cools. During the later stages of that eruption, instruments on the active rock spine measured it, sinking a noticeable amount every day. These shallow processes pull the surface downward, independent of anything happening far below. Put the 2 halves together, and you get the strange but entirely non-contradictory picture this mountain is showing now, charging far below while its shallow skin cools and sags above. The 2 are not fighting each other. They're happening at different depths on different timelines. Surface sinking doesn't mean magma is leaving. It means the top is cooling while the bottom quietly refills. This is also precisely why this mountain keeps catching people off guard. In recent years, this volcano has produced its most significant short-term jump in earthquake activity since its last eruption ended, and once again, nothing eruptive followed. More recently still, the monitoring agency had to publicly reassure residents that the mountain was not erupting after large plumes were spotted rising off the peak. Those plumes turned out to be decades-old ash from the 1980 eruption, lifted off the flanks by strong wind. Not a new eruption, a ghost of the old one. A mountain so associated with a single catastrophe that its own dormant ash, kicked up by a gust of wind, can trigger public alarm. To understand why that catastrophe still casts such a long shadow over every twitch this mountain makes, you have to go back and look at it, because 1980 is the yardstick that tells you exactly what today is not. The reason this mountain carries its reputation is not abstract. It earned it on a single morning in May of 1980 in what remains the deadliest volcanic disaster in U.S. history. The point of revisiting it now is not to frighten anyone, but to show you what an actual countdown looks like, so you can measure this week honestly. 1980 was loud, visible, and constantly accelerating. This week, by every available measure, is quiet. The reawakening back then began in March, after more than a century of dormancy, with earthquakes and bursts of steam. Then came the part with essentially no equal in the modern record. The entire north flank began to physically deform outward, not settle, not sink, bulge, as molten rock shouldered its way into the volcano's side. That bulge grew at a rate of several feet per day, and over the spring pushed the mountain's face outward by several hundred feet, something a person standing nearby could watch happen with their own eyes over weeks. Accelerating shallow deformation, ground swelling as magma climbs, is the textbook warning sign of an imminent eruption, and it is precisely the signal today's mountain is pointedly not producing. What turned 1980 into a genuine countdown was never any single measurement. It was the acceleration. For roughly 2 months, every signal compounded together. Earthquakes didn't stay faint and deep, they grew larger and crept upward. Steam explosions became frequent. The bulge swelled visibly day after day until the rock could no longer contain the pressure. Anyone watching the instruments that spring could see the trend bending unmistakably toward the surface, toward failure. Multiple independent signals all growing at once, all shallowing at once, all pointing the same direction. Hold that image, because it is the exact opposite of the flat, faint, sinking picture this mountain is showing this week. Then, at 32 minutes past 8 on the morning of May 18, 1980, a magnitude 5.1 earthquake shook the overstressed bulge loose all at once. The entire north flank collapsed in a single massive landslide, the largest ever recorded on the planet at the time. With the side of the mountain suddenly gone, the pressurized system inside was instantly uncorked, and it exploded sideways rather than upward, flattening forest across roughly 230 square miles and stripping over 1,000 vertical feet off the summit in an instant. The mountain's elevation dropped by more than 1,300 feet in a matter of minutes. Ash reached neighboring states by early afternoon and eventually circled the globe within weeks. The eruption killed 57 people. One was a young volcanologist stationed at an observation post several miles away, a distance everyone believed was safe. When the flank gave way, he had only seconds. His final radio transmission, a handful of words, became the defining human moment of the disaster. The observatory that still monitors this mountain was established in the aftermath of that morning, and it carries his name. That is the weight 1980 continues to hold over every headline this volcano generates, and it is exactly why the contrast with this week matters so much. Set the two side by side, because this comparison is really the whole argument. 1980 was a surface bulging outward by feet each day. This week is a surface sinking. 1980 was earthquakes climbing toward the surface as magma forced its way up. This week is tiny earthquakes miles below, where a reservoir is quietly refilling. 1980 was accelerating, shallowing, and inflating, 3 signals screaming the same direction at once. This week is faint, deep, and unremarkable in isolation. Everything that made the 1980 signature an unmistakable countdown is simply absent now. That's not a permanent guarantee about the future. It's an honest reading of the present. The genuinely sobering part of this story is not this particular swarm. It's understanding that this mountain has a long habit of producing false alarms, standing down every time, right up until the one time it eventually won't. Which raises a fair question. If this refilling is happening so far below, what's actually refilling it? And why does this mountain keep coming back to life more than its quieter neighbors? This mountain doesn't refill itself by accident. It sits at the surface end of one of the largest geological machines on the planet, and to understand it, you have to look offshore. Off the coast of the Pacific Northwest, a slab of ancient seafloor is being forced beneath the continent at the Cascadia subduction zone, the same fault capable of producing a catastrophic magnitude 9 earthquake, one that geologists have long warned could devastate coastal communities from northern California to British Columbia. As that slab grinds downward, water trapped within it is squeezed into the mantle above, lowering its melting point until the mantle begins to melt. That molten rock rises, and wherever it breaks through, it builds a volcano. That's the origin of the entire volcanic range through this region, a chain of peaks standing behind the subduction zone, each one fed by the same offshore engine. This particular volcano is the most active member of that range. It has erupted more frequently and more recently than its taller, quieter neighbors, which is exactly why a swarm here draws attention that an identical swarm elsewhere never would. The recharge earthquakes rattling beneath the mountain this week are the near-surface expression of that plate-scale machine grinding away offshore, the visible fingerprint of a magma conveyor reaching all the way up to touch the world we live in. There's a reason this specific mountain, rather than one of its taller neighbors, keeps generating headlines decade after decade. The molten rock it produces is a thick, high silica type that doesn't flow easily. It traps gas efficiently, builds pressure steadily, and tends to fail explosively rather than releasing gradually through gentle flows. The mountain is also geologically young and unusually active, having repeatedly built itself up and torn itself apart many times over its history. That combination, a genuinely active volcano fed by thick, gas-rich magma, is exactly why a modest swarm here draws so much more attention than one beneath a quieter, less explosive volcano. The stakes are objectively higher, and the caution is earned. So if the underlying engine never really stops, the real question isn't whether this mountain will wake up again someday. It almost certainly will. The question is how anyone will actually recognize that moment when it arrives. Scientists aren't guessing about what a genuine reawakening would look like. They know the telltale signs because this exact mountain has shown them before, and none of them require speculation or a crystal ball. A real countdown would announce itself through a specific set of interlocking changes worth committing to memory, because they matter far more than any single earthquake count. The first would be migration, earthquakes shifting from deep underground, where recharge lives, upward toward the surface, tracing the path of magma actually moving. The second would be a change in the awa, character of the shaking itself, the onset of harmonic or volcanic tremor, a continuous vibration signaling fluid and gas moving through the plumbing rather than simple rock cracking under stress. The third, and arguably the most important, would be a direct reversal of this week's headline pattern. The surface would stop sinking and start to rise, measurable inflation, replacing the current deflation trend as pressure finally reaches the shallow system. The fourth would be a genuine rise in volcanic gas, carbon dioxide, and sulfur dioxide climbing steadily as magma nears the top. And the fifth would be steam explosions, the mountain clearing its throat with bursts of superheated water and rock, exactly as it did in the weeks before 1980. Right now, not one item on that list is occurring at this mountain. What's actually happening is a faint, patient swarm far beneath the surface that continues to settle downward, the unmistakable signature of a volcano quietly refilling itself on a schedule measured in decades. The absence of every genuine countdown signal is, itself, the central fact of this story, and it is exactly why the official alert level hasn't moved. Just as important, this happens to be one of the most heavily instrumented volcanoes on the planet, wired with seismometers, satellite radar measuring ground movement down to fractions of an inch, gas sensors, and precise positioning receivers, an observation system built specifically because of what happened here in 1980. That density means the transition from quiet recharge to genuine reawakening would not slip past unnoticed. The warning signs would appear one after another, captured by instruments designed to catch exactly them, long before anything reached the point of real danger. The reason this week reads as routine isn't that anyone is failing to look closely. It's that the people watching most carefully with the best tools ever pointed at this mountain are seeing a volcano quietly refilling itself, not one rising toward eruption. So where does that leave things this week? Exactly where this mountain has stood for years. Alive, slowly refilling, sitting at a normal alert level, and producing a swarm that is far more scientifically interesting than it is dangerous. This is not a mountain counting down. It's a mountain performing routine underground maintenance, the slow work of a volcano operating between eruptions, and the surface subsidence that looks so alarming at first glance is simply the visible result of the top layer cooling, while the deep reservoir below quietly fills back up. There are a few concrete things genuinely worth tracking in the weeks ahead, the same things the observatory itself will be watching. First, the swarm. Does the rate climb toward the pace seen in past comparable episodes, hold steady at a low trickle, or fade back into silence? Second, the ground. Does deflation continue as it has for years, flatten out and stabilize, or the one genuine game changer, reverse direction into measurable inflation? Third, whether the observatory issues any public statement about the current activity at all, and if it does, whether it reaches for that one specific telling word, recharge. Until one of those signals actually changes, the takeaway is steady and honest. A volcano can shake without swelling, it can refill without erupting, it can sit at normal while its deep plumbing quietly fills far below a settling surface. That's not the beginning of the end, it's simply the sound of a living mountain, working through one more chapter in a very long story. The day a real countdown begins at this mountain will not look anything like this week. It will look like 1980, loud, shallow, and unmistakably rising, and the point of paying Close attention now, during the quiet, ordinary stretches, is so that when that day arrives, nobody mistakes it for just one more false alarm. We will be watching all the way through.